Welcome to today's Danfoss webinar, Quick Steps to Ensure Compressor Health, hosted by Jamie Kitchen. My name is Michael Beckerman, and I will be your moderator. During this 60-minute session, Jamie will focus on observations and measurements that identify and troubleshoot key parameters that affect compressor life expectancy and performance. Webinar attendees are muted, but I encourage you to submit your questions into the chat box found in the GoToWebinar module. We will answer a select number of your submissions at the conclusion of this session. Lastly, this webinar is being recorded and will be available on demand at a later date. Subscribe to the Danfoss YouTube channel at Danfoss Cool US to view that recording. Well, let's get started. I'm pleased to introduce the presenter for this webinar, Jamie Kitchen, Danfoss Engineer. Jamie has over 30 years of experience with mechanical systems, 20 of which have been with Danfoss in the HVAC industry. Jamie, take it away.
All right, so as Michael said, we're going to focus today on compressors. Now, when you focus on compressors, compressor health, making sure the compressors run correctly, they're not making strange noises or drawing too much power, really most of your focus is actually not going to be on the compressor itself. Most of that focus is going to be on other parts of the system. The reason being is that all these other parts affect the compressor itself. So whether it is the refrigerant charge, the voltage that comes to it, whatever it happens to be, these all have an effect on the compressor. So what we're going to look at today are some of the key parameters, some of the key observations and measurements, and some key steps during startup and commissioning or during preventative maintenance that can catch, identify, and remedy most of the problems that are going to cause issues down the road. Key point to remember, we're going to talk a lot about root cause or root problem today. This is the real underlying reason why something fails or doesn't operate the way it's supposed to. So on the right-hand side, you see a picture of a burned compressor. This could very well be, in fact, it is an image that is taken from one of our teardown labs. All that tells you is what ended up happening to the compressor to kill it. In this case, it overheated. It got a short in the windings or a break in the insulation. It could also be smashed up, it was flooded, whatever. But it doesn't tell you what actually caused this to happen. Even though it's an electrical problem, it could very well have been a loss of charge causing high superheat. So it's important to remember that compressors, just like us, we require certain things in order to operate and be healthy. Things like correct voltage, refrigerant charge, ascertaining proper oil charge if you've got long piping runs, making sure it comes back, things like that. So when you see a compressor that's operated for 15 or 20 years, often longer than the equipment itself, it has been operating under ideal conditions or conditions that are conducive to a life expectancy, long life expectancy. So what we want to do is we want to catch all the breaks in the chain at every opportunity to catch any issues that might come along. And in doing so, it will basically future-proof the system. It will allow you to do a startup commissioning, replace a component, preventive maintenance, whatever it is. Not only does it justify the work and the revenue that it generates, it also guarantees reduced callbacks and less time wasted on the job doing unproductive things. So let's get started then and dive right in. So let's say you've got a call and you have a system with poor airflow. Customer's going to complain about it. I got poor airflow. I'm not getting cold cool in my room. I got high humidity. There's all kinds of issues, the old hot and cold room scenario. So you go there, but he doesn't tell you anything about airflow. He just says it's not cooling correctly. So you put your gauges on the evaporator, you notice that you have low evaporator pressure. What is a good thing to do to increase evaporator pressure? Add refrigerant. So you add some refrigerant, bringing up the pressure. However, you really haven't dealt with airflow. The reason I say airflow is because over 50% of the systems that are out there have such poor airflow that it negatively affects system performance. to the point where it reduces the life of components such as the compressor. So it's very prevalent. So you replace a TXV or you do something else, but if you don't address this poor airflow, eventually something else is going to happen. The system was never fixed correctly. You could end up losing a compressor, for example, due to flood back. Now what are you going to do? You still have not addressed that root cause. This causes many issues. It is like a circular problem. There is a cost to everything. So when you don't correct these root causes, when you don't find out what is actually wrong with the system, and you just take actions hoping that it will improve it, generally speaking, you are not really creating revenue the way you could be creating it. Not to mention that you could have bad word of mouth, you could have all kinds of things that can cause issues to your reputation down the road. So what do we want to do? We want to make sure that we go through each step, we do it effectively and quickly, and we catch any problems. So looking at this little chart here, you got poor voltage, high current. You detect that high current by comparing the current draw of the compressor at a specific set of indoor and outdoor conditions with what the data sheet says it's supposed to be. And therefore, you realize this current is too high, you measure the voltage is below what it's supposed to be. If you correct that, or you replace a faulty capacitor or something else that you have ascertained is wrong, well, let's put it this way. High current increases motor temperature. Increased motor temperature reduces insulation life expectancy. It does it dramatically. So the higher the current, the warmer the winding temperature is going to be. You can cut years and years off the life of that compressor. Even though it doesn't show any outward signs, it is real and it happens. So let's start by laying the foundation. Let's look at the basics. And what I really want to talk about is superheat and subcooling. Why? Because I'm going to refer to this multiple times. And I want to point out a few things when I'm going through this. So this just isn't going to be how to calculate superheat and subcooling, even though that's what we're going to do here. Let's say you got an evaporator like you have here, being fed by a metering device, in this case a TXV. You put your gauge on the evaporator, it's 18 psig, pounds per square inch gauge. You've got R134A. Look at a chart or an app on your phone, it tells you you have a saturation temperature of 20 degrees. That means the refrigerant is changing state at 20 degrees, going from a vapor liquid to a vapor. Now, eventually, you're going to run out somewhere in here of liquid. You're going to hit the dry spot on the evaporator where you no longer have liquid, you only have vapor. And this vapor, because it's colder than the surrounding air, is going to continue to absorb heat. Now, what determines superheat generally is how or where that liquid runs out. The further back in the circuit it runs out of liquid, the longer that vapor stays in the evaporator, the longer it is going to warm up and increase in superheat. So superheat is an indication of how much refrigerant you have in the evaporator versus load. The more refrigerant you have versus load, the lower your superheat's going to be. And it is directly related to load. So there is no one superheat. You can't call me up on technical support and say, I got 8 degrees of superheat. Is that right? I have no idea. What is the system doing? What are your ambient conditions? All of these things affect superheat. So there is a correct superheat value for the conditions the system is running in. Now, let's flip the other end of the system. Let's look at the condenser. A little bit different story here. Whereas we entered into the evaporator at saturation because you had flash gas mixed with liquid come out of your metering device, here we're going in superheated. So according to the pressure temperature chart, we have 410A, it's 360 psig. We see that we have a saturation temperature of 110 degrees. So in this case, we're going to condense at 110 degrees. But we don't come out of the compressor at that temperature. We might come out at 170 degrees. All right, superheated. At least you better hope it is. So we're going to hit this condenser and we're going to cool down because the refrigerant's hotter than the surrounding air. And we're going to cool down that vapor to 110 degrees. And at that temperature, it can no longer stay a vapor with 365 pounds of pressure pushing it together. So it starts to condense. And eventually, you're going to hit the wet line in this condenser where you have 100% liquid only. And as that liquid continues to travel through the condenser, it starts to cool down sensibly. And in this case, if it condenses at 110 degrees and it leaves at 98, you have 12 degrees of subcooling. So just like with the evaporator, the longer that liquid hangs in the condenser before it leaves, the more subcooling you're going to end up having based on the temperature difference between the liquid or the refrigerant and the air. Okay, so we laid that foundation. Everybody should now understand the cause of superheat and subcooling. Let's move on to the compressor itself. So we talked about things the compressor requires in order to be happy, function correctly, and be around for a while. Couple things that are obvious. You'll notice the blue lines entering into the right bottom of the compressor or right middle of the compressor. That's your suction gas coming in. All compressors that have a built-in motor, hermetic, semi-hermetic, this is hermetic, require this returning gas to cool the motor. Either the vast majority or all of it, motor cooling, is provided by the suction gas. So when that suction gas finally reaches the motor outlet after cooling the motor, it has risen in temperature substantially before it enters into the compression area of the compressor. In this case, it's a scroll. So it's going to enter into the outside of the scroll wrap. It's going to get pushed towards the center, up and out at high pressure and temperature. So the more heat the motor has compared to how much refrigerant vapor is coming in, combined with the temperature of that vapor coming in, determines how hot the vapor is going to be when it finally enters into the compression area. So if you don't have enough refrigerant or your motor's drawing too many amps, whatever it happens to be, the temperature of the refrigerant entering into the compression area is going to climb, and so is your discharge temperature. And if your discharge temperature gets up to 280 degrees, even above 250, you start to break down the oil, you lose your lubrication, and things start to go south pretty fast. So, rule number one is when you have a failed compressor, and I say 90%, it's probably closer to 99% of compressor failures are application related. And these can be eliminated during startup and commissioning and during preventative maintenance. So you want to keep that compressor cool and dry and good lubrication going on inside. So one of the first electrical failures, if you work in a teardown laboratory, you're going to see two main things. You're going to see something like this, where a compressor overheated and it burned up and it's black and it stinks. Back in the days of chlorinated refrigerants like R12 and mineral oil, you would actually get acidic vapor coming off of these things, fumes that would burn your eyes. Today, not so much. But you can see here, there's been a lot of damage. The other one you're going to see is the opposite. When the compressor kind of got too cool, you had liquid coming back, destroyed the lubrication, and the compressor seized. In this case, we're dealing with electrical failures. A big one is overheating. It's probably one of the primary causes. So you see these burned windings here. Well, the root cause of this had nothing to do with electrical at all. It was actually a charge loss. The system, AC compressor, lost charge. You could no longer cool the motor. The returning vapor had lots of superheat. The motor overheated, and this was the end result. So what are some of the primary causes of electrical failure? Well, the easier ones to catch are poor power quality. So if you're supposed to have 240 volts and you have 180, that's a problem. If you have three-phase power and you have a huge voltage imbalance between them, that's also a problem. If you decide to hook up a three-phase compressor backwards, that's never a good idea. Also, on the single-phase stuff, if you have a weak start capacitor, you're going to have a real issue because these compressors should start up with no hesitation. So if there's a delay in start, and I'll reiterate this later, you're drawing 6 times the amperage during that. And those windings heat up incredibly fast. We already talked about loss of charge. not enough refrigerant vapor coming back to cool the compressor, excessive condensing pressure, a failed condenser fan, or as we'll see shortly, lots of other things that can drive up your condensing pressure way beyond what the compressor can handle. And then finally, moisture and acid. With POE systems and HFCs, there is no chlorine. So moisture and acid necessarily go hand in hand. In other words, with a POE system, you cannot get acid unless you have moisture. So keeping moisture out of the system and preventing it from getting in there will deal with your acid problem. All right. Now, all the things I listed here, they could have been checked during a preventive maintenance program. These are some of the things that you should be talking to your customers with in detailing how you can help them make sure this system is going to run down the road, is going to operate down the road very well and for a long time. So what do you want to check? Well, observe the compressor if it's operating. When you're there, see if it starts. We already talked about the starting with the start capacitor. There should be no delay. If it's a three-phase compressor and there's a delay, you have issues somewhere with your voltage. Usually 90% of the time, there's a problem there where you don't have enough power to overcome the pressure differential. While it's a great idea to check voltage before you start the compressor, think of a car battery. If you've lost some cells in your car battery, you can measure the voltage with no load. It'll say 12 volts. But as soon as you try and draw power from it, the voltage goes into the toilet. So make sure that when you check voltage, do it again after startup so that you know that the power supply can handle the load you're putting on it. If it's already tired and overloaded, the main supply, and you're putting another, few kilowatts on it, you might see a brownout condition localized in your area. You might see a drop in voltage, and this is going to drive your current way up. This has to be addressed. Otherwise, that compressor you just put in, it ain't going to last. All right. And of course, what do you measure it against? Measure it against the manufacturer's data. Here's a chart from our data sheet. It comes with the compressor. You can Google it and look at your phone. Essentially, you see a list of voltages here. The bottom voltage range for 60 hertz tells you that this compressor will run at nominal load under these voltage conditions. However, keep in mind, this is not for long term. This is only for transient voltages. If you try and run this compressor under high load at 190 volts for years and years and years, that motor will operate a lot hotter than it's supposed to, and eventually it will fail prematurely. Once again, motor winding temperature is critical. There is a linear relationship with motor insulation life and temperature. And the higher the temperature goes, the lower the life expectancy of the insulation goes. So there's a direct relation there. If you measure high current, and your voltage is okay, check the capacitors. Also, check your power factor. A lot of meters now come with power factor checking. And if you have very poor power factor, you will find out that you are using far more current than what your power you're getting out of the compressor. So your current goes up, your motor runs hotter than it normally would with poor power factor. And once again, make sure that compressor starts up immediately. And that goes for the fan motors too. They should immediately start. If there's any lag at all, especially if it's clicking the internal overload before it starts, that needs to be addressed. Check the start capacitor. Number one. Number two, check the voltage. Moving on, let's look at some controls. Now, when you cover technical support on the phone, you're going to get a call where somebody calls up and says, what do I set my high pressure control at? Or what do I set my low pressure control at? Well, it comes from the fact you set at a certain value. That doesn't mean that is the perfect value. That's just a value that probably fits the middle of the industry. However, each refrigerant is going to be different, whether it's 404A or R134A, 410, whatever it happens to be. What you set the pressure control at, believe it or not, is based on the application envelope. And the application envelope is the set of conditions the compressor can run at. If it stays within this application envelope, you're going to get 10 years or more out of the compressor. If you operate outside of the envelope, you will get substantially less. So you'll notice there is a dotted line and a solid line here. As the evaporating temperature drops, you will notice you get to a point where the maximum condensing temperature, and of course pressure, starts to drop. So if you want to run this thing at minus 30, you can get away with it with a 1 or 4 cylinder compressor, not so much with a 2-cylinder. But here's the important thing: superheat. It is relying on that vapor, suction vapor, to cool the motor. So with 20 degrees or less of superheat, you can cool the motor at minus 30 and 140 degrees with a 1 or 4 cylinder compressor. However, if your superheat increases to above 20, you no longer can cool that motor. Now, when does this happen? I don't know. If the refrigerant's minus 30 and you're going through an unconditioned space at 90, that's a 120-degree temperature difference. So if you have any breaks in the insulation or don't properly insulate, you can very easily pick up 30, 40, 50 degrees of superheat. If you do that and you run this compressor at one of those intersections, it is going to fail relatively quickly. So here's the rub. Pressure controls assume a specific value for superheat. It's very low. If the superheat goes up, you're going to have to reduce that value and interpolate a bit here. Like an example is on the very right-hand side, you'll see what's called RGT 68. That is a return gas temperature of 68 degrees, the maximum the compressor can take. So somewhere in there is a value of superheat above 20 and between 68 degrees. So make sure you either talk to application engineer at Danfoss or look at the guideline here and pick a correct value, right? Most of the time you can set these pressure controls to 120 degrees or equivalent pressure and they'll run just fine. All right. So we refer to the high and low pressure control. One thing that we have to be very careful about is loss of charge. Loss of charge is very devious in that a lot of times it happens quite slowly. Yes, anybody can find a leak that drains out in a couple of days. But if you have a slow leak where you're losing, 15% of your refrigerant charge a year, that's a lot harder to find. And with just a set of manifold gauges and looking at it for a short period of time, you're not going to catch it. And what ends up happening is if you look after about a year and a half or 2 years, you've lost enough refrigerant, even in an AC system, that it no longer can cool the motor. So every 2 years, you're going to have a compressor failure. So if you replace a compressor, one of the key things you need to do is to make sure the system is absolutely leak-free. Because remember, that compressor failed for a reason. Unless the system is 25 years old, it failed before its time. You need to find out why. Otherwise, there's a good chance that new compressor you dump in there is going to have the same fate in a much shorter period of time than you'd like. So as far as pressure controls go, a loss of charge drives up superheat. It drives it up dramatically. So you will lose motor cooling and a failed compressor before the high pressure cutout will catch it. The solution to this is a discharge thermostat. Put a little discharge thermostat on the discharge line about 6 inches away from the compressor. You see them quite a bit on heat pumps now. And they will protect against loss of charge. And it will protect the compressor every time against this kind of failure. Not a bad investment for something that can cost a couple $1,000s. So what are you going to see with a undercharged system? Well, there's going to be certain things that are very close to other issues, but there's going to be key differences that are going to tip you off. And I really want 3 of them to be observed before you consider adding charge. So on the left-hand side, you have a cooler. It's running with a pretty good load. You got 20-degree evaporator, plus or minus a couple degrees. You got 12 degrees of superheat. That tells me you got a pretty healthy load on there. At the bottom, you've got 12 degrees of subcooling. Again, a pretty healthy value. That tells me you have a solid column of liquid leaving the condenser, a solid column of liquid going through the metering device and being fed to the evaporator, because all three of these symptoms tell me that you have an appropriate amount of superheat. You got a strong evaporator temperature and good superheat. Now let's jump to the one on the right. Here's the issue. You still have a load. You still have those red arrows there. The issue is now you don't have enough refrigerant for the load. Now, remember back at the very start, I said superheat is an indication of how much refrigerant you have compared to the load. Well, here your evaporator temperature's dropped, and your evaporator temperature's dropped because you're not feeding it enough refrigerant. And the compressor is dropping the evaporator pressure because that's the only way it can balance its pumping capacity with what is being fed to the evaporator. And number two, because you don't have enough refrigerant for the load, your superheat is through the roof, 35 degrees, or any of those types of values. Now, that in itself only tells you you don't have enough refrigerant in the evaporator. It doesn't tell you you don't have enough refrigerant in the rest of the system, because we're going to look at several things that will cause that are not refrigerant charge related. The key that you're looking for is at the condenser outlet. If you've got 0 or 1 or some stupidly low number of subcooling, you are short of refrigerant. At this point, you can be sure with a TXV system that you have too much, you don't have enough refrigerant in the system, and you need to increase your charge. Well, here's the thing. Where'd the refrigerant go, right? Did somebody undercharge the system to start with? Yeah, that usually doesn't happen too much. If anything, they're almost always overcharged. I would really be hesitant to charge it without first finding out if it leaked or not. Because again, you can add refrigerant charge, but you're only going to be coming back again if there's a leak and doing this over and over again. So what are you looking for? Well, the customer is going to complain, long pull down times. It never shuts off. It never gets cold. The warm air is leaving the unit. What are you going to observe? No subcooling at the condenser outlet. Possibly frost on the evaporator inlet in an AC system because you're actually running at a saturation temperature below freezing. Excessive compressor discharge temperature. You're going to be way up into the mid 200s. You can look for some discoloration on top of the compressor. And if you have shortage of charge, you're going to have flash gas at the metering device. And so this means you're going to have an unstable evaporator pressure, and you're going to see hunting up and down as the TXV switches between getting fed liquid and vapor. So the next one, this is another one that can make you pull your hair out. If your refrigerant charge is okay, but you're not getting enough refrigerant into the evaporator, what could possibly be causing that? Well, a pretty good analogy to this is think back to when you were learning this stuff in school and you were taking electricity. And you get to the question where you have 24 volts or 26 volts at the control transformer. And you go to the compressor relay coil and there's 0. Well, you don't automatically put an extra transformer in there and double the voltage just to hope it gets to the relay. What do? Well, you go and figure out where the voltage went. You look at your overloads, you look at your fan switches, you look at all these things that could possibly open and cutting the power. Well, we're going to do the same thing, starting with the TXV. So if you look at this TXV, these images, these are all pictures we took through a stereoscopic microscope at the factory. And you can see all kinds of stuff in there that plugged these things that caused problems. None of this was added at the factory. Now remember, if the TXV itself is plugged, you will have subcooled liquid at the TXV, but you will have very low pressure in the evaporator. So don't assume that you have to add refrigerant charge. Check for that subcooling first. All right. Another thing is superheat adjustment. Do not adjust superheat until you have, well, we're going to talk about it next, look upstream. What else could be causing problems? If you have flash gas at the metering device, don't bother adjusting superheat. And when you do adjust superheat, one thing to take into account is the rate of change. We have TXVs that do 1 degree per turn, clockwise or counterclockwise. So if you're reducing it, your turn at counterclockwise is 1 degree per turn. We also have TXVs that are 7 degrees per turn. So make sure you know what the rate of change is before you start going nuts on that superheat spindle. All right, because it is going to happen pretty fast if it's a high value as opposed to the low value. The other thing is the system will react immediately to superheat change. As soon as you knock a degree off of the superheat, if that valve is functioning correctly and the only thing that's wrong is the superheat was monkeyed with or set wrong, you will immediately see that valve open up and put more refrigerant into the evaporator. It will still take 10 or 15 minutes to stabilize, but you should see an immediate reaction. So if you've done a couple of turns and nothing is happening, now your option list gets shorter. First thing you may want to do is hold that sensing bulb in your hand and warm it up. If you still have a bulb charge and the TXV is plugged, but a lot of pressure differential may unplug it, you might find that that big pressure difference unplugs the TXV and you get more refrigerant out of it. Otherwise, if it doesn't, it's got to come out. So pull the TXV and look at the inlet strainer, either the removable one or the permanent one that's on the liquid inlet. If it is plugged up with a bunch of crap, that tells you there's a bunch of crap in the system, and why didn't the TXV catch, or why didn't the filter dryer catch it? What do? Flush the system, replace the TXV, replace the filter dryer, or if it's got a replaceable screen, clean it and put it back in again. But make sure you get that crap out of the system. Same with a bulb charge. If you lost your bulb charge, replace the valve. There's nothing you can do about that in that case. Replace the head if you can. I mentioned it already, upstream. This is a personal favorite of mine because it caused me a lot of grief back when I was a junior tech on a Friday night. Here you have a system. You got lots of subcooling at the condenser outlet. You've got flash gas at the metering device. Don't do what I did and just add refrigerant thinking that you are low. In my case, it was a stuck solenoid valve further up that was causing a pressure drop. But if your pressure drop is greater in degrees than your subcooling, you're going to get flash gas. And I have actually seen filter dryers that were white on the outlet end because they were covered in frost. They were literally acting as a metering device and sending metered refrigerant to the metering device downstream. So a lot of times you can easily detect these with your hands or your ears and even your eyes, okay? If you can't, just put a couple of thermocouples on either side of the dryer and check it. If you're measuring a 5 or 6 degree temperature difference, that dryer is plugged. So once you get more than, whatever subcooling value you have, whatever you get that in equivalent pressure loss, you're going to have flash gas. Another topic that is important, of course, is evacuation. So when you evacuate a system, the easy part is getting rid of the non-condensable. I mean, if you're trying to get the nitrogen out of there or whatever happens to be in there, that's relatively easy. The hard part is getting the moisture out of there. Now, here's the reality. If it's a hot day and you're lucky to be down the south somewhere and it's 100 degrees outside, your evacuation to get the moisture out of the system is going to be a lot easier, because when you evacuate, you are dropping the pressure down to the point where the water starts to boil. And water boils at a much higher pressure at 100 degrees Fahrenheit than it does at 45 or 32 for that matter. So you're going to have to spend more time in cold weather in the north doing evacuation. So do yourself a favor. Dry nitrogen is your best friend. If you purge the system with dry nitrogen ahead of time, it is so bone dry, i.e. it's got a very low vapor pressure, it will scavenge moisture out of the oil very effectively. Probably better than evacuation will. So spend some time, run some dry nitrogen. Remember, dry nitrogen, not just compressed air, dry nitrogen through the system, and it will save you a lot of time in your evacuation. Number 2, do not use manifold gauges. Leave them in the truck. There are solutions today that will save you a ton of time and will give you a very accurate evacuation. Use a micron gauge, 3/8-inch hoses. If you don't have them, get them, vacuum rated, and a core removal tool. Basically, you will get 2 or 3 times the evacuation rate with those tools than you will with just your straight manifold gauges. And you will actually get an accurate picture of what your vacuum level is. So hitting 500 microns is not nearly as hard as you think it is. And if you can do that, and then you pressure test with nitrogen, you can make sure the system is dry. Also, you can make sure it is leak free, all in the same time. Okay. This picture you see here is a still that was taken from some video footage in that we did. And this was a job that I was at quite a few years ago. Now you'll notice there's some fresh stumps here, all right? Well, I had the customer cut all this stuff away. Why? Because I couldn't tell where the unit was. You know, I was expecting a tiger to come walking out of this thing or something. It was crazy. There were so many bushes around there. Well, here's the funny thing. When we removed all the vegetation, the condensing temperature of this unit dropped almost 15 degrees. Now think about that. And also, if you have a piston, and we'll talk about pistons in a second, in your AC system, and you drive that up 15 extra degrees on a hot day, you're going to flood your compressor. So once again, you got a dead compressor. Compressor did nothing wrong. It's just somebody decided to plant a bush or a hedge or put a fence around their unit, and the rest was what happened. Okay, you're going to see parts of this unit later on because the story continues, but that's essentially what we recommend here. Again, ditch the manifold gauges. Once again, HFC and POE. As much as a lot of people don't like POE oil, it has the blessing or the advantage of requiring moisture in order to cause acid. By not allowing moisture in the system, you'll get rid of the acid. So make sure if you open the compressor up, you immediately attach it to the system, preferably by bleeding nitrogen through the system and into the compressor, and then stop your purging and sprays the compressor in immediately. You will save yourself a ton of time down the road getting the compressor dry. Well, we talked about high superheat and burning the compressor up. Let's look at low superheat. What happens when we have too much refrigerant and it doesn't all boil off and makes it back to the compressor? All compressors require dry vapor free of liquid, even in a flooded system. Now, some people say, oh, squirrels can handle liquid. Yeah, they can, a liquid slug for 3 seconds. But if you get continual liquid return, you're going to dilute the oil, you're going to flash that refrigerant, you're going to wipe the lubricating oil off the main bearing, which sits right underneath the center of this scroll, and it's going to seize. And because you have that big counterweight, it's going to keep going, and it's going to smash everything to heck inside. And when you go to tear it down, it's going to sound like a maraca when you shake it. It's going to be full of bits and pieces that used to be a compressor. This picture here is from a failed scroll due to liquid return. So how do you know how to get rid of this? Well, you look for superheat at the compressor inlet. So we call this saturated suction superheat. It sounds like an oxymoron, but really what you're doing is you're calculating saturation temperature at the compressor inlet, which can be 4 or 5 degrees less than at the evaporator. And then you measure your temperature and you calculate superheat there. And on low temp systems, 10 degrees is good. On higher temp systems, maybe 12 or 15 on a cooler, and maybe 20 or even 25 on an AC system. The danger with AC systems is during dry weather where you really don't have any humidity. That lends to a problem because humidity is a huge part of the load, as we'll see in a little bit when it comes to AC. What are some of the other things to check? Well, evaporator icing. If you live in a place where you have hot and cold seasons, you have 3 times more moisture in the air in the summer than you do in the winter. And this makes a big difference, even in kitchens, restaurant kitchens, which most people think are pretty steamy anyways. there's still a lot more moisture in the summer than there is the winter. So if you set your timed defrost up for winter, you are probably only defrosting about half as often as you need to in the summer. And once ice starts to build, well, then you have a problem because the ice acts as insulation. And this drives the temperature lower and lower, and eventually you don't get enough airflow through there, causing low heat transfer. Fan speed and operation. How many fans do you have? Are they all running? Are they turning in the right direction? Trust me. Has somebody used the wrong speed tap? All these things need to be checked. Your TX bulb, is it insulated and secured? Is it hanging somewhere in the air? Is the sun shining on it? I've seen all of these things, especially with TXVs where they use one TXV in multiple capacity systems. If they're installed right, everything's fine. Well, if the TXV has extra capacity, and a lot of times they do, if it's going to flood the compressor or flood the evaporator, it's just going to do it that much more. By the way, this coil, I've seen them get so bad where they actually crack and split down the middle. Scares the hell out of everybody. All right, my favorite, off-cycle migration. You ever wonder why they put that heater around the bottom of the compressor? It's not just an easy way to burn your forearm. It's there to raise the temperature of the oil 10 or 15 degrees at least above the rest of the system. So if your refrigerant's at 60 degrees and your oil's at 75, you will never get refrigerant entering the oil. POE oil loves refrigerant. And so it will literally absorb that refrigerant vapor because it has a lower vapor pressure. And the evil thing is that refrigerant will settle to the bottom and separate from the oil. So you end up with a pure refrigerant mixture on the bottom, a mixture in the middle, and virgin oil in the top. And this will continue to absorb refrigerant until such time as the compressor decides to start. And when this happens, you get a pressure drop. All that liquid refrigerant turns to shaving cream or flies right up the crankcase centrifugal oil pump and dry cleans the upper bearings. And when it does that, you end up with a seized compressor and tear down pictures like you saw earlier. Everything is as clean as possible can be. It's just in a lot of pieces. So the solution, once again, is a crankcase heater. Between a crankcase heater and a discharge thermostat, you could probably reduce compressor failures by 90% almost. But anyways, here we have a couple different kinds. The bottom is a belly band that wraps around. The top one is an insertion type. It would go into one of our MTZ or MT or NTZ compressors. It is self-regulating voltage-wise, anywhere between 100 and 600 volts. You also have the pancake or diaper type that fit on the bottom of the compressor. They also help reduce noise, and they're very efficient. All right, so let's summarize, and let's add a few more points on what you can do during startup. So you're putting a new system in, or you're starting it up after replacing the compressor, and you're probably not going to be on a really clean job site like this one, but you're going to be doing a lot of the same thing. So number one, my recommendation, use one of these one-time jugs for recovery. They're empty, they're clean, you fill them up, and you either reuse the refrigerant or you take it in and get your money back. And there's no worries about cross-contamination with R12, 502, 11, 134, and a bunch of other stuff that you can think of. All right. The second thing is very important, weigh the charge. So if you have a system that's supposed to take 30 ounces and you pull 9 out of it and the compressor died from overheating, yeah, you have a pretty good idea of probably why it died. So what do? You spend special attention at leak checking. Why? Because I doubt somebody undercharged the system. They may have, but probably far more likely you have a leak somewhere. Find it, or you're going to have the same problem down the road with the replacement compressor. So charging. How do you charge a system? Well, you've heard the old rule, beer can cold, right? Well, when people are paying big money for Sears 16 systems, more than I probably paid for a lot of my cars, you want to make sure you have a proper charge in it, because a proper charge is 90% of the way to getting good efficiency out of it. So on the older systems with pistons, you charge to superheat. So you should be very familiar with this chart. On the left, you've got indoor temperatures. On the right, you have your wet bulb. Charge according to the outdoor dry bulb and indoor wet bulb. Mark the superheat and charge until you have that equivalent superheat. With TXV or adaptive system, you charge to subcooling. So you go with the outside temperature, indoor wet bulb, and you charge to pressure and subcooling. Keep in mind, these are not universal values. This is a SEER 13 system. You charge a SEER 16 system with the same dry bulb and wet bulb, and you're probably only going to charge it to 380 and maybe 8 degrees of subcooling because condenser is much larger. Finally, some of the things people overlook. If you are starting up a new unit, the grommets on the compressor have probably all been torqued down. Bring them up and loosen them until they are torqued to spec value. It is very important that compressor does not vibrate because you want to keep all the pipes attached to it. Same goes with tandems. See these two tandems, the bottom of them? They have hard plastic grommets on them. The rails themselves are floated on the rubber grommets, but the compressors are hard fastened to the rail. Why? Because you do not want them to move independently of each other. They are attached together. If they move independently, it will break and you will get lots of oil everywhere. And if it is a tar and stone roof, you will be replacing the roof because it will do a ton of damage. All right. Remember that unit that had the jungle growing around it? Well, here was the terminal box. And guess what we found in it? A snake. The snake was long gone. It was dead. But once we pulled it out, we saw this. Well, obviously, you're going to replace the start contactor relay. You're going to replace the capacitor. We also cut back and replaced it with new wiring. Okay, why? Because it's cheap insurance. You're putting something in there that's $1,000 or a couple $1,000, right? I have no idea if this stuff's going to work properly or what problems it could cause. So replace it along with the filter dryer as well. And I was really glad when the technician had all this stuff with him. I didn't even have to bring it up. He just automatically did it. Make sure you check the pressure control, same as on preventive maintenance. Test the function. On the Danfoss controls, you have a test button. With an automatic relet, just push the automatic reset, just push the test function, and you'll see the contacts move. On manual reset, push the reset button along with the test button, and the contacts will move. They should not stick. And if you see sticking or you see some black oxide burning on there, all right, clean them or replace the control, or during preventive maintenance, clean the contacts with a little bit of emery cloth. You can pull this cover off as well as see through it, clean them up, dry them out, and put it back in there. It's a great fix to keep the system going. Finally, once again, airflow. If airflow is not correct, no other measurement that you take is going to tell you anything important other than the fact that you have low airflow. So make sure you verify airflow. Use the manufacturer's specification. Most of the time, you are doing it with static pressure, but however you do it, verify airflow is what it's supposed to be. All right, because if you have poor airflow, you have poor air conditioning. You have poor dehumidification and cooling. You are not going to have a happy customer. And nothing else you do is going to improve the system until you correct that airflow. Trust me on this one. All right. And once again, never add refrigerant until you verify system charge with either superheat, subcooling, and with superheat, subcooling, and evaporator temperature and pressure. Okay. And make sure you verify that airflow. If your airflow is low, so is your superheat going to be. All right. So don't add refrigerant just because you see a low evaporator temperature. Finally, make sure the condenser has good airflow. It is getting outside air and not regurgitated air from another condenser or an exhaust outlet from a factory, whatever. Condensers are dumb. They don't know what the outside temperature is. All they know is the temperature of the air that's going into them. So if you're rejecting air out of a condenser at 110 degrees on a 90-degree day, and it enters into the outside upstream condenser, the condenser is going to act like it's 110 degrees outside, and it's going to burn a lot more energy. Thank you, everybody, for your time. I appreciate it.
Okay, let's open things up to the questions. Appreciate everyone who had submitted one. Jamie, if you're ready, we can jump right in.
Let's do it, man.
All right, cool. So the first question is regarding the low charge slide.
Yes.
Would I have a good subcooling if dirty filters and or coil? I guess if we had a dirty filter and or coil.
Yeah, I mean, if you're talking airflow on the evaporator, and let's say with an adaptive meter device like a TXV, yes, you can have lots of subcooling. But if you lose your airflow, really all you're doing is reducing heat transfer into the evaporator. So the metering device is actually going to close up and inject less refrigerant into the evaporator, which means there's actually going to be more refrigerant in the rest of the system because you don't have it in your condenser. All right. On a piston system, really you're going by superheat. So if you're running with a blocked air filter or reduced load, what you're going to see is, if you measure your indoor wet bulb and dry bulb, and you're supposed to have 18 degrees of superheat, and you see 4, and your evaporator temperature is 33 degrees instead of 45, that's more likely what you're going to see. In this case, you are actually going to have about the same amount of subcooling, maybe a little bit less in the condenser, because again, the amount of subcooling you have at the condenser with a piston-like system, the subcooling drops with an increase in outdoor ambient condition. Why? Because the hotter it is outside, the more refrigerant it's going to inject into the evaporator. So really, your evaporator air load does not affect subcooling nearly as much as refrigerant charge or the outdoor ambient temperature.
Cool.
Good question, by the way.
Next question is it good practice to use a starter kit for the compressor or a start kit?
When you say it's a good idea, I use them as a last resort because as much as they are beneficial, they are also hard on the motors. Now, keep in mind, every time you start a motor and you apply torque to it, you are flexing the winding. You're literally, if you did it in slow motion, you would literally see there'd be a dimensional change to the winding. So if you put a honking amount of torque on this thing to overcome a load, number one, you got to ask yourself, why is this a problem? What is causing this? If it's a poor voltage, then, can you correct the voltage? If not, fine. But keep in mind that over time, you are going to disturb that winding and it will not last forever. So yes, it's a good Band-Aid solution as a last step. I would not recommend just putting them on anytime you need them. Okay, anytime, whether you need them or not, because again, there's always a cost to that in the form of how much stress you place on the motor winding.
Okay. Is the target superheat for the evaporator or the compressor?
Well, it depends. Usually you go by evaporator, but look at the literature. It will specify where you take your evaporator superheat. I always look at the compressor. Why? Because that's what I'm concerned with. If my evaporator superheat, or sorry, my saturated suction superheat is where it's supposed to be, right, in line with the indoor and outdoor temperatures, then I am good to go, right? So I always look at it that way. Some people prefer to use the evaporator superheat, but again, the manufacturer will specify where to measure it when you're dealing with charts. If I don't see where to take that measurement, I default to the compressor. Some people may use the evaporator. Either way, if you can ascertain that you have a correct range of superheat, you're good to go. All right. I just like doing it at the compressor because that's what I've always done, and it's pretty damn easy to get to most of the time.
Okay, next question. Why do we require more superheat at higher evaporator temperatures?
Good question. One thing, you're trying to protect the compressor and by not overheating it, but at the same time not flooding it. And when your evaporator temperature drops, the challenge now is to keep the compressor cool. Because just because you're running a -20 ice cream freezer doesn't mean that your condensing temperature outside is any lower, right? You still may be running a 95 or 100 degree ambient, 110 or 115 or 120 degree condensing temperature outside. What ends up happening is your compression ratio goes up. The motor has to work more. Well, at the same time, the density of the refrigerant vapor returning to the compressor goes down. In other words, you have less pounds per minute of refrigerant going over the motor to keep it cool. You also have less chance of flood back in very low temp systems like that because of the lower mass flow. So you can get away with less superheat in a low temp system, and at the same time, you're protecting the compressor. In AC systems, the concern is if you have a sudden change in load in an AC system, let's say you've got a zone control system, or people turn dampers off, or something happens. If you suddenly get a load issue and your load drops, it's much easier to get flood back out of an AC evaporator and into the compressor. And if that's the case, we're looking for a little bit high superheat. Why? Well, here's the thing. When you're running an AC coil, the temperature difference between the AC refrigerant and the air is much higher. You run your coil 45 degrees, your house is 75 degrees, maybe 72 at the lowest. There's a 30-degree difference between the evaporator, refrigerant, and the air. In refrigeration, what temperature difference do you have? 8, 10 degrees? It's like a third the size. So you can't expect to have very, very high superheat when your refrigerant temperature is not that much colder than the air. Whereas in an AC system, we're focused on dehumidification, and we want gobs of temperature difference. The lower the better to dehumidify the air. So it is not uncommon to run 16 or 18 degrees of superheat under very high load with a TXV. And guess what? Those TXVs that come from the factory, they're set for 2 degrees a lot of times of static superheat, whereas a refrigeration valve is set for 7 degrees of superheat. And that means that the refrigeration valve won't even open until you have 7 degrees of superheat, whereas the AC valve will open at 2 degrees. So it's not uncommon to expect higher values of superheat at the evaporator. It's also not uncommon, if you have a change in humidity, for that to drop very quickly, especially with a piston. All right. I hope that answers your question.
All right, great. That's all the time we have for the Q&A section, but please check our Twitter page at Danfoss Cool US, and Jamie will be answering the rest of all the questions we received today.
Yeah. I'll also go back and research a little bit of those questions you asked me. And because I'm just pulling answers off the top of my head, but I do have literature on that. I will go back and look at them. If I find a better answer, I will provide it to you.
Okay, great. So yeah, take a look at our Twitter page and give us a follow for those answers to all the questions. Yeah, so thank you, Jamie. And again, thank you to everyone for attending today's webinar, Quick Steps to Ensure Compressor Health. We encourage you all to connect with both Jamie and Danfoss for more learning opportunities, videos, tips, tricks, and tools. As you can see on the screen, our Twitter, our YouTube, and LinkedIn. Jamie will be hosting one down, 4 to go. You'll be hosting a few more webinars over the next few weeks. So if you're interested in more, please visit danfoss.us and scroll down to the latest news section to sign up for those as well. So again, thank you all, and have a great rest of your day.
Thank you.